Thank you, Anuma, for this introduction. So I'm Avinanda Chakraborty. I'm a final year PhD student in Presidency University under Dr. Suchitana Chatterjee. So I'm going to talk about a totally different topic from all the speakers of today. So for the next couple of minutes, I'll discuss my work on constraining Quasar feedback models with the Atacama large millimeter array probing synapse signals. So last day from Priyanka's talk, we already have heard about synapse effect. So there are two types of synapse effect. One is thermal, one is kinetic. So our work is totally based on the thermal synapse effect. So just for a quick reminder, so thermal synapse effect is basically the inverse Compton scattering between the hot electrons and the CMB black bodies, CMB photons and the hot electrons present in the line of sight, which cause a spectral distortion in the CMB black body spectrum. So this is a famous image of AGN feedback. This is an observational evidence of AGN feedback. This is from McNamara-Nelson 2017, and this is a combined image of Chandra, Hubble, Space Telescope, and VLA. So in our work, we are interested to probe the synapse effect from quasar feedback, basically, and spatially. We are trying to see that what could be the what could the effect in the synapse effect if there is an involvement of jet. Okay, so there are several works who have talked about synapse effect from quasar feedback, but these are all theoretical works. So now let us look at what happens, what is the situation of direct detection. So the synapse effect is so small that it is very hard to detect. So it is said that these two are the two telescopes. One is the Atacama large millimeter array, and another is the next generation VLA. These two have the resolution of detecting the synapse effect, but so far there is only one such detection, direct detection of quasar feedback via synapse effect. This was back in 2019 by Mark Lacey and his team. So there is no such detection after that. So here comes our work. So we are here to provide one template to the observer so that whenever there is one detection, the observer can directly match it with our results. So for that, we have used cosmological simulation. We have used SIMBA simulation. This is from Dove et al. 2019. This is a gizmo meshless finite mass hydrodynamic cosmological simulation. And in the right hand side, we can see a visualization of hydrodynamic simulation. And it has the box size of 50 H inverse megaparsec. It includes dark matter, gas dynamics, radiative cooling, star formation, black hole growth, and most importantly, 4 different feedback prescriptions. So this is the reason why we are interested in this particular simulation, because it involves 4 different feedback prescription, which also involves one jet mode of feedback. So there are 3 mode of feedback: jet mode of feedback, radiative mode of feedback, and X-ray mode of feedback. And these are the feedback prescriptions. So all feedback includes all of them: radiative, jet, X-ray. No jet feedback includes only radiative, and no X-ray feedback includes radiative plus jet. So I'll keep you reminded about this again. About these 4 prescriptions. And another is the 4th one is the no feedback, which includes none of them. So for our work, we have selected one high redshift and one low redshift snapshot from the SIMBA simulation. So this AGN feedback is mostly studied in X-rays. So this is a study of X-ray of AGN feedback by one of our collaborators, Dr. Rudjani Choudhury. And this is she has also used this same simulation. But in our work here, we are trying to propose one new avenue to study AGN feedback via synapse effect. So for our work, we have selected 2 representative sets of black holes. One is the most massive, one is the most active. Basically, most active is the most luminous one because accretion rate is proportional to luminosity. So we have selected 2 representative sets of black holes for our work. So in the right hand side, we can see the table where we can see the black hole parameters of our work, which we have used for our work. So, but here I'm going to present the results only for the most massive ones. So these are the theoretical SZ maps for most massive black holes at 4 different feedback modes. This is at redshift 1. So these maps are made 100 kiloparsec by 100 kiloparsec map at 320 gigahertz, and the number of pixels are 500. So this map is the SZ map, theoretical SZ maps for no feedback. And when we are adding the radiative feedback, that is for the no jet feedback, we are getting slightly increment in the SZ signal. But when we are further adding the jet mode of feedback, so that is in this feedback mode, we have radiative and jet, then we are getting a significant suppression in the SZ signal. So we are getting a drastic suppression in the SZ signal. We can see from the results. And again, further adding the X-ray feedback, we are getting further suppression. So from these 4 maps, we can see that the high signal we are getting from the no jet feedback, that is for the radiative mode of feedback, and the lowest signal we are getting from the all feedback. This is at redshift 1. So this work has already been submitted in AppJ. This is in under review. So next, let us look at the low redshift results. This is the similar as the high redshift. Here also we are getting the highest signal from the no jet feedback and lowest signal from the all feedback modes. So here also from these two results, these two redshift results, we can conclude from here that jet is acting as the most driving force in case of SZ signal if we are using this simulation. Also from here we can also conclude, also notice one interesting thing, that the upper panel for both the cases we can consider it as the non-jetted one because it doesn't have jet feedback mode, and the lower panel can be considered as the jetted AGNs. So we can from both the results on both the panels, we can conclude that we are getting different SZ signals for jetted and non-jetted AGNs as well. So that can be more clearer when we look at the radial profile. So these are the radial profiles at redshift high. This is at redshift 1, high redshift. This is at low redshifts. So here, these are the radial profiles for the same black holes, same theoretical maps I have just shown. And we can see that the upper two radial profile, that is for no feedback and no jet feedback, the profiles are very consistent, and also for the lower two profiles, these two are also consistent for both. This is a similar case for both the redshifts, but we can see from here also a drastic suppression when in the signal when the jet is added. So from here also we can conclude that jet is playing a significant role in case of SZ signal. So next we try to make the mock SZ ALMA maps. For that, we have used the CASA software and its SIM-ALMA task, and these are the CASA SIM-ALMA parameters values we have used to make the mock SZ ALMA maps. So for the theoretical ones also, I haven't presented I haven't presented the results for the most active black holes because we are getting the similar results. So let us look at the simulated ones. So this is also result of most massive black holes. So here and these are the mock ALMA SZ maps for the same theoretical maps I have shown previously. So this is at redshift 1. So here this is the mock ALMA SZ map for no feedback, and we are getting signals as the signal for this map, and also likewise the theoretical maps when the radiative mode of feedback is added, the signal is getting even higher. We can see it from here. But when the jet mode of feedback is added, for these two cases, we can see that the signal gets so suppressed, that is, it is going beyond the detection limit of the threshold limit of AGN detection, ALMA detection, sorry. So we can see from here that when the jet mode is present, we are not able to detect the SZ signal with ALMA. This will be more clear if we look at the fidelity maps. So fidelity maps are basically the SNR maps or the signal to noise ratio maps, and can clearly see prominent signals for both no feedback and no jet feedback at a high redshift, but there is no such signals at all for the all feedback and no X-ray feedback. So it is very clear that we are not getting any signals for when the jet is present for ALMA. So next, let us look at the low redshift maps. So these are the low redshift mock ALMA SZ maps, and here also likewise the high redshift maps, we are getting the similar detection for no feedback and no jet feedback. We are getting detection for no feedback and no jet feedback, but here also the signal gets so suppressed in case of no X-ray. When the jet is present, basically, we are not able to, it is going beyond the threshold limit of ALMA. So this is getting more clear from the fidelity maps also. We are getting signals here, but there is no such signals. But if we pay the attention to the fidelity maps for both low redshift and high redshifts, we can clearly see that in case of high redshift, the signal is better. The ALMA SZ signal is better than the low redshift one. So this is one important point we have found. And also next, we tried to see if there is any frequency dependence or the band dependence in the SZ signal. So we further check for the SZ signal at three other different another frequency. This is at high redshifts. So here I am showing the fidelity maps for no feedback and no jet feedback, because other twos are anyway doesn't have any signals. So here for the high redshifts, we can see that there is no such significant differences if we vary the frequency. But where if we look at the low redshift maps, you can see that especially for the no feedback, we are getting better signal when the frequency is reduced, it is getting decreased. So for lower frequencies, we are getting better signals for the low redshift frequency, low redshift systems. Okay, so this is the summary of my work. So for all the systems, for the theoretical maps, we have found that we get an enhancement of the SZ signal when there is radiative feedback, and the signal gets suppressed when the jet mode of feedback is introduced in the simulation. And for mock ALMA maps, we have found that with the current prescription of jet feedback, the signal goes below the detection threshold of ALMA. Also for mock maps, we have found that the SZ signal is higher for high redshift systems. And also we have found that for lower frequency bands capture more of the signals at low redshifts. So thank you for listening, and thank you. I would like to thank to the organizer for giving me this opportunity, and especially to Shadab for all the cooperation. Thank you.